Hello and welcome back to the Renewable Energy Technology course, the lecture series on wind turbines. I am Miro and we are still at lecture 1, the basic aerodynamics and major types and operational principles of turbines. And we have reached now section 3 of lecture 1, where we will focus slightly on the main types and exactly the operational principles of turbines. The sections 3 and 4 here, together with practical fluid dynamics, are somewhat overlapping. A short reminder for what the power coefficient is about. Please don't forget and be careful with the words and terminology that is being used. The Betz limit is what defines and what proves the maximum possible power coefficient. The Betz limit for any single stage energy conversion device, doesn't matter how it looks like and what the fluid is, actually is a maximum of 59%. Not more than that energy is possible to be extracted. The actual real power output by any practical energy conversion device, however it looks like, would be expressed by such kind of an equation, representing the available energy in the fluid with all kinds of losses or inefficiencies, whether aerodynamic, hidden behind the CP, the power coefficient, or mechanical or electrical losses, or so on. The CP should not be confused with the coefficient of performance commonly used in the refrigeration industry. The simplest possible type of turbine would be the drag force one. And the simplest drag force turbine would be the one that uses flat plates, shielded from one side. We will come back to this in the history review in lecture 3. While the other side is exposed to the wind, maybe also the structure is helping to channel the wind through the device. So hopefully this side advancing against the wind is ideally shielded or behind the wall, while the other side of the rotor or the flat blades here are experiencing the full power of the wind. This is the Persian type, the so-called Persian type of ancient windmill. There have been also recorded Chinese devices which didn't use shields, but rotating plates here to decrease the drag force on the other side of the rotor. The drag force devices that we do use today are, first of all, the very common cup anemometer. This is how we measure wind speeds. This is a drag force turbine. Or the Savonius rotors. The drag force on typical bodies can be exploited actually to rotate a turbine or to drive a rotor, thus extracting energy from the fluid. If we have a flat plate with its flat section facing the wind, the drag coefficient would be approximately 1.1. If the edges are a bit rougher of the flat plate, the drag coefficient would slightly grow. If we have a typical hemisphere cut and with the hollow part facing the fluid, with the rounded part facing the fluid while the hollow section is backwards, the drag coefficient would be somewhat around 0.33. If we turn around the cup with the hollow part facing the fluid, the drag force coefficient would be approximately 1.33. And this is exactly what the cup anemometer is exploiting. But let's first look at the simplest case. That would be the ideally shielded turbine, where the blade advancing against the wind has an approximately 0 drag force in the best case. The undisturbed wind coming from here, and the blade that actually performs or extracts the energy travels with the wind. So the wind exerts the drag force, which represents the thrust, and drags with it or pushes this section of the rotor that actually produces or extracts the power. The drag force can be represented by a typical drag force equation where the velocity is now r, actually the velocity that the blade or the flat plate here is experiencing, and that would be the subtraction of the speed of the blade itself from the speed of the undisturbed fluid. The faster this blade moves, the less force the actual wind would be able to exert on it. The equation is like this, and we see that actually the power coefficient is a function of the tip speed ratio. This means that if we move faster, we would not be much more efficient. There should be some kind of an optimum in this equation. And we can solve it and find out that actually the ideally shielded flat plate drag turbine would be maximum 16% efficient, not more than that. And this is at approximately tip speed ratio of 0.33. Now moving to the real case, or that would be the cup anemometer, a drag force turbine where there is no shield, and of course it's impossible to shield very nicely any part of the rotor, but the rotor that actually the part of the blade that moves against the wind hopefully has a very low drag coefficient. That would be the cup with its convex part facing the wind. However, the real velocity that it faces is the summation of the undisturbed actual wind with the translational velocity of the blade. And this would be the drag force exerted on this part of the rotor. The other part of the rotor now moving with the wind, again, it's easy to describe the drag force there, but it depends on how fast again the rotor is moving. Because if u, the translational velocity, is too high, there would be actually no force exerted on this part of the blade. The equation is slightly more developed, but it's again very easy to handle it, and we see that the power coefficient, if we extract it and represent or insert here the tip speed ratio, being the ratio of these two velocities, we'll see that the power coefficient is a function of a little bit complex function, but a very clear function of the tip speed ratio. And drawing the line of this function will show us that at approximately tip speed ratio of 0.165, the maximum performance of this turbine can be achieved at these specific conditions, and that would be 8%. So such turbines are absolutely not good as energy conversion devices. They can reach not at all anywhere close to 59% efficiency, which we saw is the maximum possible for the best case. But they are actually very good as wind speed measurement devices because it's a smooth function of the performance or the power extracted with this turbine as a relation related to the wind speed. The Savonius rotors are other types considered to be drag force devices. However, there is a certain lift force here that acts on the blades thanks to the fact that they're actually curved plates. There are two major types of Savonius rotors. The simple ones, we can call them as a solid rotor, simply a curved plate. And the more advanced ones can be called split Savonius rotors, where like two halves of a drum, of a barrel, are moved halfway against each other, so that actually the flow passes inside those blades. And the fact that they are curved plates helps to develop some kind of a lift force. The Savonius rotors are able to reach slightly higher CPs than the common drag turbines, and tip speed ratio above 1. They can rotate faster, or the tip of the blade can rotate faster than the actual wind speed. In modern turbines, we will try to use the lift force, and we are very much obliged to use the lift force if we want the turbine to be efficient. We saw that with the drag force there is not much of a performance that can be achieved. Now, in relation to the airplane wing, we can definitely use the same kind of profile, the wing slender profile of a streamlined body, to develop a lift force. However, in the airplane perspective, the wing is supposed to lift up all the mass, while it doesn't actually move. It simply moves together with the entire structure against the major flow of the fluid. In the case of turbines, this wing, or we're actually looking at the cross-section of the wing towards the axis of rotation, or the center of rotation, the blade will have to propel itself towards this side. When the main wind is coming from here, and the imaginary wind that the blade creates by simply moving through the air is actually the speed of its translational motion, u, which can be expressed in this way, as if a wind was coming towards the blade, just because it moves through the air. The product of these vectors is simply the vector sum, or the resulting actual wind reaching the blade would be the vector sum of the undisturbed wind approaching the blade and the translational motion of the blade. The propelling force, or the actual force that performs or extracts power from the wind would be represented by the projection of the forces on the vertical here axis, or the y-axis. And it is unfortunately the difference between the projection of, on the x-axis, of the lift and drag. The drag is a stopping force, while the thrust force is useless, simply bending the blade and the machine should withstand it somehow. It is the summation of the lift and drag. And you see, in terms of an airplane, the development of the lift force is very easy. So you can lift tons of mass in the air at not so very high speeds, while the wind turbine, not being at all able to utilize very high speeds, actually will need to develop enormously high lift and use only its small projection on the plane of rotation, minus the stopping force of the drag, the projection of the drag force, in order to produce any kind of motion. The blade of the horizontal axis wind turbine would be very long if we want to sweep a large area, and now would need to be composed of different sections, because the fact that it's rotating around a center here means that the different sections are experiencing different translational velocities, which convert into different tip speed ratios. Now the V2, the speed of the fluid reaching the blade being the same, but the translational velocity being different, actually produces completely different velocity triangles, which actually forces us to dimension this blade by looking at the different sections and each of them having different profiles. This can be related also to an airplane wing. However, the airplane wing will not actually have different translational velocities. Its different profile sections would be simply governed by the fact that the root part will need to carry the load of the tip part of the blade. While in the wind turbine, it's pretty much the same situation. The root parts, besides the fact that it has to carry all the load, it will also need to be designed for a completely different velocity triangle. And this is how this can be done. The so-called blade element theory is used to properly design the wind turbine blade, cutting the blade in small sections, designing each of them for its proper governing conditions. How exactly the profile looks like and at what angle it is fixed along the radius, along the axis of the blade, is defined by the velocity triangles at that section. And if we look from the top of the blade towards its root, we will see that it actually is built up different profiles and it's twisted. The root of the blade is thick, solid, at high angle, while the tip of the blade is slender, very, very streamlined profile, almost sitting along the axis of rotation at a close to zero angle of attack. What actually happens behind the turbine, and this is a reason of using the lift force, which as a result slightly deflects the fluid, is that continuing its path behind the rotor, the fluid starts to rotate. The situation is not one-dimensional anymore, so this is the first stage of adding complexity or a real-life scenario of what really happens with the turbine. Now, having an actual device composed of blades that would extract energy from the fluids by rotating themselves, so the thing has to move, otherwise there is no work being done. But by moving, actually we deflect the fluid in the opposite direction. So the flow behind the turbine rotates in the direction opposite of the rotor rotation, of the turbine rotation, slowly moving away from the turbine and rotating. This rotation is called simply a swirl or rotational wake. The swirl is difficult to handle, and it also interacts with the undisturbed flow. Behind the turbine, the streamlines defining the boundary between the disturbed and the undisturbed flow would actually be boundary zones where the two flows or the shear levels start to interact. This also combines with the swirling rotational wake and produces actually turbulence behind the rotor. The mixing between the disturbed and the undisturbed shear layers we can simply call shear turbulence. It is a bit difficult to express, but if we try to express the rotational wake, we're actually halfway towards also having the shear turbulence in terms of mathematics. It is difficult, really, to calculate the rotational wake, and the predecessor of Betz, that would be Frederick Lanchester in England, actually got stuck exactly with this thing. He tried to develop the one-dimensional theory, or the basic theory of the wind energy conversion by actually looking at the rotational wake. And it was difficult for him to represent it mathematically. It happened only when Ludwig Prandtl, the German physicist, the very, very famous aerodynamicist, and actually the British guy Hermann Glauer, despite his German name, developed the proper mathematics and managed to describe what actually happens with the rotational wake. It can be done by cutting the flow tube behind the turbine in small ring sections, each of them, let's say, infinitesimally small, and developing the mathematics for each of those rings, looking at the fact that the fluid is slightly swirling in the opposite direction of the rotor. Now, we don't need to get nasty, don't get afraid. We're not going to look very careful at these equations. I'm simply showing how this can be done. The pressure developed, or the pressure differential developed by the rotor, would need to be expressed now in terms of the rotational motion of the fluid. The thrust, again, would need to be expressed as a function of the rotational motion. Then the torque, which is the useful force developed by the rotor, is again a function of those values for each section of each ring of the rotating tube. An angular induction factor can be introduced in the equation, and finally describing the power developed by each section of the ring as a function of the tip speed ratio and the angular induction factor. This translates into the power coefficient actually being, again, a very complex function of the tip speed ratio, also for the advanced lift force turbines. The actual induction and the angular induction factor can also be expressed as functions of the tip speed ratio. The result of this is that real turbines, doesn't matter how good they are on how high lift forces they can develop, actually can never reach the best performance of the Betz limit, which was defined for the best case ideal scenario when there are no losses. The rotational wake and the turbulence that it exerts actually are losses. And slow-moving rotors are subjected a lot to these types of losses, while the fast-moving rotors would be able to approach the Betz limit. And we can see this here in terms of numbers. At very low tip speed ratios, that would be slow-moving rotors, the maximum possible power coefficient when we take into account the rotational wake is far below the Betz limit. While fast-moving speedy rotors at tip speed ratios close to 10 would be able to approach almost the actual Betz limit for the best possible performance. This results into defining the optimum number of blades, together with the fact or taking into account the solidity of the rotor, and knowing that fast-going, few-bladed rotors are inherently more efficient. Now we managed to prove actually that the fast-rotating rotors will be more efficient. And this is just an example of how a turbine can be designed and how a blade in its different sections along the radius would look like, the twist angles, the profile chords, and so on, for the three good examples of typical turbines that we might have today. That would be the multi-bladed wind pump, the three-bladed machine, and the two-bladed wind turbine. A summary of what we learned in this section: drag force turbines are very simple and robust, but definitely they are not good as wind energy converters. They are not efficient at all. In order to be efficient, the modern turbines will have to use the lift force, and they should have few blades with highest possible tip speed ratios. There are other problems related to very fast rotating machines, and of course we will look into those in the next sections. The swirling wake and any kind of turbulent field behind the turbine means a loss. And actually this is the major aerodynamic loss that any kind of real actual device would experience. It can be minimized again by fast-moving, fast-rotating rotors. But there are also additional losses which we will look into in the next section.